If there were no subcooling, saturated liquid from the condenser would try to cool itself down to a lower saturation temperature to match the progressively lower pressure in the liquid line. The only way the saturated liquid could cool itself down is for some of it to flash into vapor. Whenever a liquid flashes into vapor, heat energy is needed for the vaporization process. Almost all of the heat supplied to the flashing process is from the heat in the saturated liquid itself. This cools the remaining liquid down to the new saturation temperature associated with the new lower pressure caused from the pressure drop. This type of cooling is referred to as adiabatic cooling because there is no net loss or gain of energy in the liquid. Liquid line flash gas is detrimental to system performance. Metering devices will experience a mixture of liquid and vapor instead of a solid column of liquid at their entrances, and the liquid-vapor mixture decreases the capacity of the valves. When liquid flashes in the liquid line, it also leaves less liquid to flash in the evaporator. This takes away from the refrigeration effect and adversely affects system capacity. Excessive liquid line flash gas may even erode the needle and seat areas of some TXVs. Pressure losses that take place in the liquid line are the result of either friction pressure losses or static pressure losses. Friction pressure losses are caused from refrigerant flowing either through tubing, dryers, elbows, or even a sight glass on its way to the metering device. Some of the fluid energy is used to overcome friction from the sidewalls of the pipe or from an obstruction such as the filter dryer. This lost energy in the fluid causes a loss in pressure, which is why liquids must be subcooled before experiencing these pressure drops to prevent liquid flashing. Proper line sizing, short runs, and unobstructed accessories like clean filter dryers can prevent excessive friction pressure drops. Static pressure losses occur in the liquid line whenever liquid has to flow uphill through vertical piping. A vertical column of liquid naturally has more pressure at its bottom than its top due to the weight of the entire column of liquid. Whenever liquid from a condenser or receiver must be piped uphill, there will be a static pressure drop as the liquid climbs higher in the piping. This is in addition to the friction pressure losses from the pipe sidewalls as the liquid climbs. Different refrigerant line sizing has no effect on static pressure losses from vertical lift, as it is dependent on the weight of the refrigerant itself. The amount of total subcooling needed is system dependent. The more friction or static pressure drops associated with the lines and accessories that carry the liquid in the system, the more need there is for liquid subcooling to prevent liquid line flash gas. Subcooling can be accomplished by numerous methods. Common methods include liquid suction line heat exchangers, ambient air, direct expansion mechanical subcooler heat exchangers, or increasing the pressure of the liquid line. On receiverless systems, simply adding a little more refrigerant to the system can increase subcooling, but this is usually not recommended because of added inefficiencies that may occur. There are several ways to subcool liquid refrigerant. One way, often called ambient subcooling, is to sensibly cool the liquid in the bottom of the condenser, removing sensible heat from it. Ambient subcooling, however, cannot be maintained at a given level with only air-side controls. Subcooling this way takes up valuable condenser volume with subcooled liquid at its bottom, since condensing cannot occur in this area. The more de-superheating and liquid subcooling that is done by the condenser, the less useful condenser area there is. This causes higher high-side pressures and compression ratios, thus lower efficiencies. A more efficient way to subcool liquid usually is to use liquid pressure amplification. Using this technology, liquid refrigerant entering the liquid line is pressurized by a small centrifugal pump. By increasing the pressure of the liquid refrigerant, the associated saturation temperature is raised, while the actual liquid temperature remains the same. The liquid therefore becomes subcooled and will not flash if exposed to pressure drops in the liquid line. Because the liquid centrifugal pump motor is external to the refrigeration system and the impeller is driven by a revolving magnetic field, the system is completely sealed and negligible energy and heat are added to the system. Liquid pressure amplification technology has given refrigeration systems capacity boosts while saving electrical energy. In the past, high head pressures and temperatures were artificially maintained in a refrigeration system so it would function well at low outdoor temperatures. Air conditioning and refrigeration systems were designed for an outside temperature that would not be reached any more than 2% of the time in the life of the system, and if reached would occur only a couple hours at a time. The selection of the condenser was then made based on this seldom reached condition. Today, designs are specifying larger condensers with condensing temperatures 10 to 15 degrees Fahrenheit above the ambient. The significant energy savings from lower compression ratios and possibly increased subcooling of liquid negate the higher costs of a larger condenser. Another term for attaining the lowest possible high side pressure is floating the head pressure. This involves letting high side pressures vary depending on outdoor ambient conditions. However, if one tries to float the head pressure with the ambient, the lower head pressures common in low temperature systems will require more subcooling for the same pressure drops in the liquid line in order to prevent flashing. This phenomenon happens because the refrigerant pressure temperature graph is non-linear. This is one of the reasons why liquid pressure amplification is incorporated in a system when the head pressure is floated with the ambient, because the LPA ensures that the liquid line pressure and saturation temperature are always higher than the actual liquid temperature. For an evaporator to operate at peak efficiency, it must have a high percentage of liquid to vapor ratio entering the evaporator. It has been discovered that TXVs work with much less pressure drop across them than expected as long as pure liquid is supplied to them. Consequently, condensing pressures and temperatures have been allowed to float downward with the ambient temperature. With an LPA pump, subcooling and pressure can be maintained at a constant at the metering device. Overfeeding and underfeeding by the expansion valve, which dramatically affect the efficiency of the evaporator, will then be minimized. Superheat suppression can be used in conjunction with liquid pressure amplification. The superheat suppression process injects liquid refrigerant into the compressor discharge line or inlet of the condenser. This liquid usually comes from the same centrifugal pump used in the LPA process. This liquid flashes to vapor while cooling the superheated discharge gas closer to its condensing temperature. As a result, less surface area is required for de-superheating. This leaves a more efficient condenser because of the increase in useful condensing surface area, which increases the overall performance of the system.